So now let's say I give you an equilateral triangle. We all already know from the do now that an equilateral triangle is also equiangular. And when we drop down that altitude, that top 60-degree angle gets split into two 30 degrees. Now, I have already labeled a side length. I said that WY is side length S. Unknown side. It's called S. Okay, well, because we have a 30, 60, 90 triangle and we want to find the area of this, do we agree the area is still half the base times the height? Okay, because it's equilateral, if one side is S, do we agree that all the sides have to be S? So the base of this is also S. But now I need to find the height. So I'm going to use one of these 30, 60, 90 triangles. And I know opposite the 30 is x, opposite the 90 is 2x, opposite the 60 is x root 3. So my equation to solve for x is going to be, over on the side, 2x equals s. Everybody with me so far? I need to solve for x. How do I solve for x? Divide by 2. I'm going to divide by 2. So that means x is equal to s divided by 2. So one side length divided by 2. So that's this right here. And then what will the height be? Well, the height will be x times root 3. Well, our x is our side length divided by 2 times root 3. So we would represent it by that, s over 2 root 3. Do we agree that's our height now in terms of s? So now I'm going to plug that in. We have s over 2 root 3. And now we multiply. So my area is going to equal, I have to multiply all my numerators together. So 1 times s is s. S times s is what? Don't tell me 2s, please. Don't tell me 2s. S squared. S times s is s squared. We still have that root 3, right? What about now we multiply the denominators? 2 times 2 is 4. So we have s squared over 4 root 3. That root 3 could be in the numerator. It could be on the outside of the fraction. It really doesn't matter as long as it's not in the denominator. And guess what? This is the formula for area of an equilateral triangle. What do you think S represents? Side length, exactly. S represents side length. So let's write this out. Scroll down. Area of an equilateral triangle will be S squared over 4 root 3. I'll say S equals side length. We ready? Okay, area of a regular polygon. All right, we need to remember what does it mean to be regular when we're talking about polygons. What does it mean to be regular? Good. In order to be regular, it has to be equilateral, but it also has to be something else as well. Excellent. In a regular polygon, all sides are congruent and all interior angles are congruent. So in order for a polygon to be considered regular, it can't always be just equilateral. It must be equilateral and equiangular. question for you. An equilateral polygon is equiangular. An equilateral polygon is equiangular. How many people say always? Equilateral polygon is equiangular. How many people say sometimes? How many people say never? Okay, you're right, it is sometimes. Can somebody think of a polygon that is equilateral but not equiangular? So something, a quadrilateral that we learned about. Something where all the sides are congruent but the interior angles are not all congruent. A rhombus, excellent. All right, a rhombus has all sides congruent, but the inside angles are not all congruent. Can somebody think of a polygon that is equilateral and equiangular? A square, excellent. All right, so in a regular polygon, just write down these new vocabulary words and then I'll explain to you what they mean and how we'll use them. So in a regular polygon, P-E-N-T-A, O is considered the center. OA is a radius. And OM is an apothem. So there has been, for as long as I've been teaching, a debate of whether it's apothem or apothem. Tomato, tomato, whatever you want to call it, it's all good. Okay, definition. A radius of a regular polygon is a segment joining the center to any vertex. Okay, so we are now introducing these vocabulary words into regular polygons. Center, radius. Where have we used these vocabulary words before, center and radius? With circles, and it's not far off. These still are in reference to a circle, but when we're talking about a regular polygon, what we're envisioning every time we discuss this polygon is that there is a circle circumscribed about the regular polygon. So the polygon is inscribed in a circle. And so when a polygon is inscribed in a circle, the circle has a radius, the circle has a center. So the radius and the center of the circle circumscribed about the polygon is the same center and the same quote-unquote radius of the polygon. So I told you that a radius is a segment from the center to one of the vertices. Well, if the circle circumscribed about isn't from the center to one of the vertices also the radius of the circle, and the center of the circle is the center of the polygon. So that's where we're getting these vocabulary words from, these circle vocab words that we're now applying to a regular polygon. Because we're saying whether it's drawn or not, we are envisioning a circle circumscribed about this polygon. Okay, important observations about radii of regular polygons. All right, a radius of a regular polygon is a radius of a circle circumscribed about the polygon. A radius of a regular polygon, this is a big one, bisects an angle. So it bisects the angle that it touches. So every radius we draw in, so you know how we're drawing it to the corners? It bisects all of those angles, splitting it into two equal angles. If all of the radii of a polygon are drawn, oh, I wrote drawn, the polygon is divided into, let's see, let's draw all these in. All right, so I drew in all of the radii. What shapes have I created inside this polygon now? Triangles. What is special about these triangles? What kinds of triangles are they, I should say? They're not equilateral because all radii are congruent. Does that necessarily mean they're congruent to the bases also? No. So it's not equilateral, but they are. What? I heard mumbling. Isosceles. They're not equilateral, but they are isosceles triangles. And a step further, since it's a regular polygon, aren't all the bases congruent? So what's the relationship between all these isosceles triangles? They are congruent. So we split them into congruent isosceles triangles. So if all the radii of a regular polygon are drawn, the polygon is divided into congruent isosceles triangles. All right, so there's one vocab word we have not discussed yet, and it's a completely new one. You've never seen it before, the apothem. An apothem or apothem, an apothem of a regular polygon is a segment joining the center to the midpoint of any side. But we had learned something, right? Didn't we learn way back when we were dealing with circles? If a segment coming from the center bisects a chord, what else is it in relation to the chord? Excellent, Taya. It's also perpendicular. So not only will the apothem bisect the chord, it will also be perpendicular to it. All right, important observations about apothems. Only, this is a big one, only regular polygons have apothems. So does that mean a rectangle has an apothem, yes or no? No, rectangles do not have it. Do squares have it? Yes. Do equilateral triangles have it? Yes. Do isosceles triangles have them? No. Good. An apothem is a radius of a circle inscribed in a polygon. That's not so important for you to know. Oh. Inscribed in. An apothem is the perpendicular bisector of the segment it touches. And last thing, all apothems are congruent. Okay, in the past, at this point, I would have you derive by yourself a formula for finding the area of a regular polygon, but I'm going to save you that brain power, and I will just tell you the area of a regular polygon is going to be half the apothem times the perimeter. So A is the apothem, and P is the perimeter. Are we ready to do some sample problems now? All right, so it says a regular polygon has a perimeter of 40 and an apothem of 5. Find the polygon's area. Well, we just learned a formula to find the area of a regular polygon. The area will equal half the apothem times the perimeter. Well, they're telling us the apothem is 5 and the perimeter is 40. Now remember what we discussed in the beginning of this chapter. Do I have to multiply in order? No, so I don't need to take half of 5. What is the better option here to take half of 40? Half of 40 is 20. So now we're left with the area being 5 times 20, which is 100 units squared. All right, number 2. It says an equilateral triangle has a side 10 centimeters long. Find the triangle's area. So in the past, we would have drawn a diagram and we would have said 10 and 10 and 10. And then what would we have done? Have to draw down an altitude. Is that still acceptable? Yeah, it's absolutely still acceptable. But now we found a way to make it a little shorter. What have we found? We found the formula for the area of an equilateral triangle. Area equals side squared over 4 root 3. So our area is going to be our side length. Well, what's our side length? 10. So it's going to be 10 squared over 4 root 3. Now, students sometimes forget their basic algebra skills, and they'll take that 10 over 4 and simplify it. No, no, no. All right, according to PEMDAS, do we do exponents or division first? Exponents. You must do the exponent first before you divide or simplify the fraction. So I have to do 10 squared first. What is 10 squared? 100. So this is 100 over 4 root 3. And what is 100 divided by 4? 25. So the area of this equilateral triangle is 25 root 3 centimeters squared. We ready? Okay. So this one we for sure need a diagram. It says a circle with a radius of 6 is inscribed in an equilateral triangle. Find the area of the triangle. Okay, so I'm telling you the circle is inscribed in the triangle. So which one's going on the inside? Is the circle going on the inside, or is the triangle going on the inside? The circle. It says the circle is inscribed in the triangle. So basically the circle is inside the triangle, inscribed inside. So let's get that going. And now they're saying the radius of this circle is 6. There are so many places I can draw in a radius. Does anybody know where it would be the best place to draw in the radius? So like I could draw it like this, right? Isn't that a radius? It is a radius, but is that helpful to me? No. Maggie? Excellent. I'm going to draw that radius straight down right where it touches the triangle. Because remember, way back when we were talking about circles, if a radius touches a tangent, what does it make? When a radius touches a tangent line, it makes right angles. All right, so now this is 6. Now this was a special kind of triangle. What kind of triangle was it? Equilateral. So what does that mean about the triangle? All the angles are 60. Okay, so right now we still need to do more work. We do not have enough to find the area of this triangle. So what I'm going to do is I'm going to go to the center, and from the center, I'm going to draw radii of the equilateral triangle. Okay, I'm going to draw the radii. How do I draw radii of an equilateral triangle? I draw it to the vertices, to the corners. Just down there, just on the bottom. Why have I chosen just to draw the radii on the bottom? Excellent. So now we can make a 30, 60, 90 triangle, because remember the radius of a regular polygon bisects the angles it touches. So that 60 will get split into two 30s. So I'm going to use one of these triangles, and I know opposite the 30 is x, opposite the 60 is x root 3, and opposite the 90 is 2x. What does x equal? X is equal to 6. So this x root 3 has to be 6 root 3. Do we agree that this side is also going to be 6 root 3? So what's the total length going to be of one side? 12 root 3. Well, since this is an equilateral triangle, what does that mean for all the other sides? They're all 12 root 3. All right, now, was I asked to find the side length? No, what was I asked to find? Area, but don't we have a special formula? Area equals side squared over 4 root 3. And now we know the side length, so area will be 12 root 3 squared over 4 times root 3. What do I have to do first? I have to square the 12 root 3 first before I divide by 4. So now I will go over to the side of my paper and say, okay, well, 12 root 3 times 12 root 3. 12 times 12 is 144. Root 3 times root 3, 3. Excellent, whole number 3. Did anybody multiply this? 144 times 3? You can do it for me. I'm sorry? 432. 432. So now we're going to have the area is equal to 432 over 4 root 3. Okay, so now we're going to take that 432 and divide it by 4. So we're going to get area is equal to 108 root 3 units squared. All right, let's do another one of these types of problems. Can I go on to the next problem? All right. So it says find the area of a regular hexagon with sides 18 units long. You know what? I did a huge disadvantage here because I drew in too much stuff for you, and on a test, I will not draw anything in for you. So let me show you what I would give you on the test. I would just give you a hexagon and nothing else. So it says the sides are 18 units on. So what does that tell us? Every side is 18. Because it's regular, and I'm asked to find the area, what formula am I going to use? Area equals half apothem times perimeter. Since it's regular, I can use that formula. So what do I need to figure out now? I need to figure out the apothem and the perimeter. Is perimeter easy? Yes, the perimeter is just going to be 18 times 6. So that's easy. Now the apothem, not so much. Who remembers what is an apothem? How am I going to draw this? Maggie? Good. I'm just going to draw straight down to the midpoint of that side. Here's an apothem. And what is it going to do to that 18? Split it in half. All right. Not much help finding the length of it, right? At least we got it drawn, but it's not really much help in finding the length. So what I'm going to do is I'm going to draw in all the radii of this hexagon. And how do I draw in the radii? From the center to where? The corners. And now what have I created? Triangles. How many triangles? 6. We had done this. Who remembers what the relationship is between all of these angles? Anybody remember all those angles, those by the main center point? Angles can't be isosceles. All the triangles are isosceles, but the angles, they're all congruent. And why are they all congruent? Again, going back to the circles unit, what did we learn? We had learned if the chords are congruent, remember, because this is a polygon inscribed in a circle, because it's regular. Every time we have a regular polygon, we just think of it as a polygon inscribed in a circle. So if the chords are congruent, what else are congruent? The central angles are also congruent. If the chords are congruent, then the central angles are congruent. And doesn't that mean also the arcs are congruent? So how will I find one central angle if I know that they're all congruent? How do I find one central angle? All these central angles together make what? 360. All central, do you guys want me to write this down to refresh your memory? All central angles make full circle 360 degrees. So if all the central angles together make a full circle of 360 degrees, how would I find just one of them? You got it. So we're going to say one central angle will be 360 divided by 6, which is 60. All right, so now the 60 in the triangle we're using gets split into two 30s. And now what kind of triangle do we have? 30, 60, 90. Opposite the 30 is x, opposite the 60 is x root 3. So what is the apothem here? Nine root 3. You got it. All right, so now let's go into our formula. Area will equal half 9 root 3. And then the perimeter is going to be 18 times 6, which is 108. Should I take half of 9 root 3? No, what should I do? I should take half of 108, which is 54. And then we're going to do 54 times 9 root 3, which is 486 root 3 units squared. There will 110% be questions like this on your test when it comes. We're going to take this one out. This was a challenge one. We'll take that out. I want you all to try independent number 6. It's very similar to the problem we just did. Oh, wait, no. It's a little bit different because now I'm telling you the radius of it is 12. So try this one and then we'll go over it. Are we ready? Are we stuck? How many people think they knew how to go about this? Excellent. All right, let's see. So I'm drawing a diagram. All right, so now they're saying not the side length, they're saying the radius of the hexagon is 12. So what I'm going to do is I'm going to draw in all of the radii. And we know these are all 12, 12, 12, 12, 12, 12. All right, we still have to do what we did last time. And remember that all of these central angles are congruent. So how would I find just one of them? Good. One central angle will be 360 divided by 6, which is 60. And then I'm going to go and I'm going to take one of the triangles and I'm going to drop down an apothem. And that 60 will get split into two 30s. And then we have a 30, 60, 90 triangle. And now in this 30, 60, 90 triangle, we know opposite the 30 is x, opposite the 60 is x root 3, and opposite the 90 is 2x. Am I going too fast? Good. All right, so now we know 2x has to equal 12. So that means x is equal to 6. So one side, the x is 6, which means the whole side has to be 12. And what about the apothem? How long is that? 6 root 3. Do we have everything we need to find the perimeter? Do we have everything we need to find the area? Yes. So answering a few questions. Find the length of one side. Well, one side is how long? 12. Find the length of the apothem. Well, we said the apothem was 6 root 3. So now we want to find the area. So area will equal half the apothem times the perimeter. So area will equal half 6 root 3, and then the perimeter will be 12 times 6, which is 72. I'd probably do half of 6. So now we have 3 root 3 times 72. Yep, you're good. Area is equal to 216 root 3 units squared. All right, so your homework is listed. I will post it on Google Classroom. We are done for the day.